In this session, we're going to see how to use the binomial theorem. What it is a tool for expanding binomials. And when I say expanding binomials, I mean if we were asked to expand something like x plus y the quantity squared, what we might do is FOIL it or use the pattern for the square of a sum and end up with x squared plus 2xy plus y squared. That's no big deal when your exponent is 2. If we start to consider something like x plus y the quantity cubed, though, then the process, we could do it. We would multiply x plus y the quantity squared, expand that out as we just did, and multiply by another factor of x plus y. And once we collect all our like terms, we would end up with x cubed plus 3x squared y plus 3xy squared plus y cubed. And it's cumbersome, but we could do it. If we consider something like x plus y to the fourth power, now it's starting to get out of hand. And here's where the binomial theorem can come into play for us. Before we expand x plus y to the fourth, though, I'd like to look at the kind of the anatomy of what happened when we expanded x plus y the quantity cubed. First off, the first term is x cubed. And then in the second term, we have that x again, but it is squared. The exponent is dropped by 1. In the third term, we have x without an exponent, which means it's to the first power. And then finally, in the fourth term, we don't even have an x, which means that we can think about it as being x to the 0 power. In other words, the exponent on x is decreasing by 1 in each successive term. Alternatively, the exponent on y, let's look at the second term, is 1. And in the third term, it's 2. In the last term, it's 3. We can extrapolate and say, well, in the first term, we can call it y to the 0. And so we see that the exponent on y is increasing for each term. Now just looking at these patterns, for x plus y to the fourth power, we might conclude that we would have an x to the fourth in the first term, and then an x cubed, and an x squared, an x to the first power, which I'm just going to write as x. And then in that last term, x to the 0, I'm just not going to write the x at all. Looking at the pattern of the y's, for the first term, it would be y to the 0 power, which I'm not going to write. In the second term, we'd have y to the first power, which I'll just write as y. And then we're going to keep increasing the exponent on y squared, y cubed, and then y to the fourth power. And that process should kind of make sense to you. Something to note, in x plus y the quantity cubed, the expansion of it, if we add the exponents in any one particular term on x and y, it always adds up to 3, which matches that it was x plus y the quantity cubed. Recognizing that, for instance, y is y to the first power, and x is x to the first power, we have that same thing going on with the exponents in the expansion of x plus y to the fourth power. Now I'd like to turn our attention to the coefficients. In x plus y the quantity cubed, there's no coefficient for the first term, none written, so it must be a 1. In the second term it's a 3, in the third term it's a 3, in the fourth term it's a 1. Let's look back up to the x plus y quantity squared. The first coefficient is 1 because there was nothing written, and then a 2, and then a 1. And if you paid attention to Pascal's triangle, then we would recognize that the coefficients in the expansion of x plus y the quantity squared are the same as the entries in row 2 of Pascal's triangle. Remember, we start counting at 0. Likewise, for x plus y the quantity cubed, the coefficients are the third row, or row 3, of Pascal's triangle. The fourth row of Pascal's triangle is 1, 4, 6, 4, 1. And as it happens, those are going to be the coefficients on the terms in the expansion of x plus y to the fourth power. Adding together all of the terms gives us the expansion of x plus y to the fourth power. So for each of these, the instructions would be expand. And what I'd like you to do now is expand x plus y to the fifth power using what you just saw about exponents and the coefficients coming from Pascal's triangle. So pause the video and do that. And what you should have gotten was x to the fifth plus 5x to the fourth y plus 10x cubed y squared plus 10x squared y cubed plus 5x y to the fourth plus y to the fifth. Now I want to point out something. If this were x minus y, the quantity cubed, then instead of pluses everywhere, we would end up with negative signs, subtraction, in front of the terms where the exponent on y is odd. With that in mind, I'd like for you now to pause the video and expand y minus 2 to the fourth power. Okay, if we walk through this carefully, using Pascal's triangle, we'll have coefficients of 1, 4, 6, 4, and 1. In the first term, we're going to have y to the fourth, and then the powers of y decrease in all the successive terms until I finally get y to the first power, and then I'm not going to write the y to the 0. For the second term, however, it's a negative 2 that we're going to take to our various powers. Of course, in the first term it's 0, in the second term it's 1, and then so on, in such a way that for any particular term, the two exponents on y and now negative 2 will add up to 4. And then just to make sure that we have these terms identified, I'm going to go ahead and put plus signs in between, but as you might see, some of these are going to change. So for our first term, which is 1 times y to the fourth times negative 2 to the 0 power, we're just going to call that y to the fourth. Our second term is 4y cubed times negative 2 to the first power. Well, if we multiply that 4 by the negative 2, we get a negative 8. And then the y cubed is our variable. In the third term, we've got 6y squared times negative 2 squared. Well, 6 times negative 2 squared, that's 6 times 4. And so our third term is actually 24y squared. Fourth term, we've got 4 times negative 2 cubed times y. Negative 2 cubed is negative 8. Mix that with the 4, we have negative 32y. And finally, our last term is 1 times negative 2 to the fourth power. And so that's going to be plus 16. And this is how we deal with numbers if they are part of the binomial, right? They mix with the coefficients that we have from Pascal's triangle, and since they're all one term, we multiply the numbers together. Now let's shift gears just a little bit. Recall that Pascal's triangle has rows 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, etc. has a representation using combinations. And so, for instance, the row 3 of Pascal's triangle, 1, 3, 3, 1, can be written in terms of combinations: 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So when we expanded x plus y to the fifth power and wrote down our coefficients of 1, 5, 10, 10, 5, 1, those could have been expressed using combinations as 5 choose 0 with x to the fifth, and then 5 choose 1 as the coefficient on x to the fourth y, 5 choose 2 on x cubed y squared, and so on. You may notice some similarities in a couple of the numbers here. It's kind of subtle, but the bottom number in the combination, like 5 choose 5, has a 5 at the bottom, and the exponent on y in that term, the last one, is 5. When we're dealing with 5 choose 4, on the y, the exponent is 4. 5 choose 3. On the y, the exponent is 3. And you may notice that pattern for all the terms. And it's a legit pattern. And then remember that what we said a few minutes ago is that the exponents on x and y for any single term will add up to 5. And so that helps us to know what to put for the exponents on x, or the first factor. But also they decrease starting with the exponent that you see in the original, right? X plus y to the 5th power. That 5, by the way, is also apparent. It's 5 choose 1, 5 choose 2, 5 choose 3, 5, etc. Okay? So this generalizes to x plus y to the nth power is equal to n choose 0 times x to the n plus n choose 1 x to the n minus 1, remember it's going to decrease by 1, times y to the first, if you like, plus n choose 2 x to the n minus 2 times y squared plus dot dot dot, bunch of terms, I don't know how many because it's n, all the way up to n choose n x to the 0 power y to the nth power. And what you may notice is, yeah, the number in the bottom of the combination is the exponent on y, just as we saw before. It's also showing up in the exponent on x. You see, when it's n choose 1, the exponent on x is n minus 1. When it's n choose 2, the exponent on x is n minus 2. And so the most general way we can write this is we can say it's the sum as I goes from 0 to n of n choose I times x to the n minus I times y to the I. That sum for x plus y to the n is the binomial theorem. And as that I increases, so does the bottom number in the combination notation and the number that we're subtracting from the exponent on x and the number that is the exponent on y. And just to make it abundantly clear, the exponent x plus y to the n is the n as the upper limit of the summation and is the n in the combination and is the number that starts the exponent on x. It is also the number of the row that we would use in Pascal's triangle. So when we can use this is in the next example, which is find the coefficient of a cubed z to the 9th in the expansion of a plus z to the 12th power. Well, according to the binomial theorem, a plus z, the quantity to the 12th power, is equal to the sum, as I goes from 0 to 12, of 12 choose I times a to the 12 minus I times z to the I. Couple of things. One, we're only asked for the coefficient. We aren't asked for the whole term, and we are certainly not asked to expand the whole thing out. That would just be awful. It would be boring is what it would be. We're asked for the coefficient, and the term we're looking for is a cubed z to the 9th. Okay, so we're looking for the term that where a has an exponent of 3 and z has an exponent of 9. Since the exponent on z corresponds to the I, the index of summation, it is the case in this case that I is equal to 9. So we're actually looking for the term 12 choose 9. And the term itself would be 12 choose 9 a to the 12 minus 9, z to the 9, right? That a cubed z to the 9th that we're after. But all we're really after, being that we're after the coefficient, is 12 choose 9, which my calculator tells me is 220. Yep, it's that straightforward. Next, find the sixth term in the expansion of 3x plus 2, the quantity to the 8th power. Well, again, let's recall from the binomial theorem that 3x plus 2 to the 8th power is the sum as I goes from 0 to 8. Well, now look, we have 3x in place of what has been x, or in the last example, a, in the first term, right? So we have this combination business, 8 choose I, no getting around that. But then this 3x is going to be to the 8 minus I. So it's the quantity of 3x that goes inside the parentheses. And then we have our 2 to the I. So whatever's in the first term goes in the first factor, right, after the combination with the exponent. And whatever's in the second term inside the parentheses for the binomial, it becomes the second factor with the exponent. Now we're asked for the sixth term, so we may be tempted to say that I is equal to 6, but that just wouldn't be true. We start counting at 0. And so for the sixth term, I is actually going to be 5. And so what we're looking for is 8 choose 5 times 3x to the 8 minus 5 times 2 to the 5th power, which is, of course, 8 choose 5 times the quantity of 3x cubed times 2 to the 5th power. And so we need, what? We need 8 choose 5, right, from the calculator. We need 3 cubed, because that's what's going on with that exponent. And then we need 2 to the 5th power. Multiply all those together, and my calculator tells me that the coefficient is 48,384. And that's just the coefficient, but we were asked for the term this time, not just the coefficient. So 48,384 times x cubed is the sixth term. Next, we're ramping it up a little bit. Find the coefficient of x to the 4th in the expansion of x minus 2 over the square root of x to the 10th power. Well, let's see what our the variable portions. Well, let's see what kind of our terms would look like. We'd have 10 choose 0 x to the 10th power times, the thing to the 0 power, so I forget the second term. The next term, though, is going to be plus 10 choose 1 x to the 9th, right? That exponent is going to drop by 1. But then we have like times negative 2 divided by the square root of x. And now all of a sudden we see that the exponent, when we simplify, isn't going to go the way we expect it's going to go. The exponent on x to the 9th times negative 2 over the square root of x is actually going to be, let's see, 9 minus a half. So this is going to be x to the 17 halves. And so they're going to mix in strange ways here. So what we need to do is we need to figure out just when is the exponent going to be x to the 4th power. And folks, we might just start guessing. Like, suppose I guess that the term is going to have x to the 5th. So, the exponent of x is going to be 5. If that were the case, then the exponent on negative 2 over the square root of x would also be 5, because remember, the exponents are going to add up to 10, 10 being the exponent on the binomial under consideration. And so I'm not going to write equals because I'm not concerned with the negative 2 right now. But ultimately, this would be x to the 5th divided by x to the 5 halves, which would turn out to be x to the 5 halves if you do the subtraction of those exponents, which is less than x to the 4th. Let's go with x squared, see what happens there. If the term has an x squared in it as the first factor, then the negative 2 over the square root of x would have an eighth power. That would give me x squared divided by x to the fourth power, and now we're looking at x to the negative 2, and we just went in the wrong direction. I'm not saying you have to guess around at everything all the time. I'm just showing you a thought process, so I'm not just pulling the right answer out and you wonder where it comes from. Well, let's go with x to the eighth. Then the factor, negative 2 over the square root of x, would have an exponent of 2. And that would give me x to the eighth in the numerator, and then x in the denominator for x to the seventh. But we want it to be x to the sixth. Let's cut to the chase now. What we're going to be looking for is the term where we have x to the sixth power, and then negative 2 divided by the square root of x to the fourth power. Remember, those exponents need to add up to 10. And then the coefficient, the combination coefficient, is going to be 10 choose 4, because remember, that bottom number matches the exponent on the second factor. So I see this term is going to be 10 choose 4, and I'm using equals now because I'm actually writing the same thing, times 2 to the fourth x to the sixth divided by x squared. And if you notice, the exponent on x, once we simplify, is going to be 4, just as we were hoping for. We were asked for the coefficient, and so all I really need is 10 choose 4 times 2 to the fourth, which is 16. So my calculator tells me that this is 3,360 as the coefficient on this term. Next, we're going to see how this extends to trinomials. And this is our last example. Find the coefficient of x squared y to the fourth z cubed in the expansion of x plus 2y minus z, that quantity to the ninth power. I'm not going to write down anything like the sum of anything like that, but what I want to do is I want to consider a term in the expansion of x plus y to the fifth power. You may remember that the third term, or if you don't remember, it's in your notes. The third term is 5 choose 2 x cubed y squared. Now let's consider this 5 choose 2. If you recall, 5 choose 2 has a formula, and it's actually 5 factorial divided by 3 factorial times 2 factorial, and it's an interesting phenomenon that those numbers in the denominator of the factorial expressions are the same as the exponents on x and y. This generalizes to the trinomial case. And so we are actually going to have 9 factorial. Now that 9 is coming from that it's, x plus 2y minus z to the ninth, divided by 2 factorial times 4 factorial times 3 factorial. Those factorials matching the stated exponents of the desired term. Now that's, let's say, the standalone coefficient. But the term is actually x squared times 2y to the fourth power times negative z cubed. Now we weren't asked for the term, we were only asked for the coefficient, but we have to take into account the number, and in this case, the sign. So we have to take into account the 2 in 2y and the negative in negative z. So the coefficient is going to be negative because negative z has an odd exponent. And then we've got our 9 factorial divided by 2 factorial times 4 factorial times 3 factorial times 2 to the 4th power, which my calculator tells me is negative 20,160. Once again, we were just asked for the coefficient, which we have found. Last thing I want to point out, when you put this in your calculator, 9 factorial divided by 2 factorial times 4 factorial times 3 factorial, make sure that your calculator knows that all those factorials in the denominator are in the denominator. They're free and come in pairs. Practice safe math and use your parentheses.